Okay, these are notes on conservation of mechanical energy, and in most of your notebooks they're going to go on 14R and also 14L. I'm going to go pretty quickly through this, so you might need to pause your notes periodically so you can copy them down. We're going to call this conservation of mechanical energy. And you need to draw your vertical line for Cornell style, and so I'm going to do that for you in my notes. And first of all, let's review forms of energy. We've studied three forms. One is gravitational potential energy, one is kinetic energy, and one is elastic potential energy. All three of those forms of energy are mechanical energy. In this particular case, we're just going to be talking about gravitational potential energy and kinetic energy. Both of these forms of energy are forms of mechanical energy. The law of conservation of energy states that in a closed system, which we've already previously defined, and this is a system with no non-conservative forces. What we call these are like friction and air resistance, these forces that pull energy out of a system. Mechanical energy is conserved. So what this means, if there is no friction, or air resistance, the sum of all the mechanical energy does not change. Okay, so to show you an example of this, we're going to use a roller coaster, which is similar to the lab that you just performed. And I'm going to draw a roller coaster, and I'm going to draw a couple of things. First of all, I'm going to skip down a number of lines. I'm going to skip down 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. So 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. Okay? So here's where I'm going to start my roller coaster. And I'm going to make my roller coaster go up 8 lines. So it's going to go up 1, 2, 3, 4, 5, 6, 7, 8 lines. It's going to end up right here. And then it's going to go down to 2 lines above my 9. And then it's going to go up to 4 lines. There you go, like that. So then I'm going to draw this big hill. Then I'm going to come back down. And then I'm going to go back up. And then I'm going to come back down again. Okay, so it's kind of a weird looking roller coaster, but this is what it is. This hill is going to be 20 meters high. It's a pretty big hill. This hill is going to be 5 meters high, and this hill is going to be 10 meters high. Okay, so this is 0, position 0. This is position 1, and this is position 2. That's 10 meters high. I'm also going to put a car from the roller coaster up here at the top of the highest hill. And the mass of this car is going to be 1,000 kilograms. And the velocity at the top of the hill is going to be 0. You know how when you go on a roller coaster, the chain drags you up to the top of this first hill, and then you wait for a minute, and you have 0 velocity. So that's what happens here. Okay, so conservation of mechanical energy says that this car, when it travels through this roller coaster, its mechanical energy is constant. What that means is at any particular place on the roller coaster, mechanical energy, which is equal to UG, gravitational potential, plus kinetic, plus even elastic potential, these are all constant. So the sum of all three of these anywhere on this roller coaster is equal to the sum anywhere else on this roller coaster. Now, gravitational potential is a relative energy, and so we're going to say the ground is 0 gravitational potential. Okay, so here's a statement. ME0 is equal to ME1, which is equal to ME2. This is conservation of energy. That means that ME0, which is equal to UG0 plus KE0, there isn't any elastic potential, so I'm not going to put it, is equal to ME1, which is equal to UG1 plus KE1, and that's equal to ME2, which is equal to UG2 plus KE2. Okay, this is all true in a closed system. Let's put true in a closed system. Okay, I'm going to do an example of this problem in the next video.